Hello everyone. In this section we are dealing with the image processing techniques. In the previous video we have seen how to process an image using system generator blocks. In this video we shall proceed with the image processing techniques. We have several image processing techniques like image thresholding, image negative image, image enhancement, contrast stretching, image segmentation, the edge detection, canny edge detector, Sobel gradient, blurring the image, and so on. We have many image processing techniques. So we should consider in this section some of the fundamental and basic image processing techniques. So we'll get an idea how to deal with images and implement using system generator tool. So first I am considering the image negative technique. So in image negatives, what happens is that a color image is entirely converted into its negative format. So this is how a graph between the output negative level pixel input pixel looks like. So this is the negative transformation. So when the input pixel is 0, the output pixel must be L minus 1, where L represents the total number of levels of a pixel. For example, you have considered an 8-bit image. The pixel values range from 0 to 255. So we can say L equal to 256 because L equal to 2 power 8 equal to 256. So we have 0 to 255, that is nothing but 0 to L minus 1. It is the range of a pixel. In the original image, if the pixel value is 0, then the corresponding output pixel of the image negative must be L minus 1. And when the input pixel value is L minus 1, the output level of the negative image must be 0. This is the basic transformation graph of image negative. So first we shall deal with this. This is the equation. S represents the output pixel value and R represents the input pixel value. So L minus 1 is the highest value of the pixel. So in our case, if we are considering the 8-bit image, we have 0 to 255. So we shall now proceed with the implementation of this technique in Xilinx. So this is the basic block diagram for our image processing model. So we have the image from file and the pre-processing block, the gateway blocks, and the post-processing and the output. So no changes I have done. The same model is pasted here. And first you need to do is that you need to initialize the sample period st equal to 1 divided by 384 into 512, as 384 by 512 is the input image size. So first let's run the model and see for the output. I do one thing, I will keep the simulation time as 1 second to save time. So this is the output we got, and this is our input. So okay, our model is fine. And now to implement the image negative model, we need to add some blocks which satisfy this equation s equal to L minus 1 minus R. So this is our R. From the gateway block we'll have the input pixels representing R, and the output of the gateway block are the pixel values representing S. So inside the gateway blocks we need to add system generator blocks so that we can implement L minus 1 minus R. So as equation suggests, we need to have two add sub blocks, one for L minus 1 and another for L minus 1 minus R. So first I will add the add sub block. For simplicity, I am considering the latest to be 0. So we need to have the subtraction and the output. Here we are considering the fixed point representation as total number of bits equal to 8 and binary point at 0. So the same must be defined here. Unsigned and 8 bits and 0. Okay. We have one subtraction here, and for L minus 1. So now we need to implement L minus 1 minus R. So for simplicity, I will consider one add sub block, so that I will give the constant as L minus 1, which is equal to 255 as here in this case. So only one block will be required, instead taking two subtractor blocks for L minus 1 and then minus R. So I will keep a constant with L minus 1. This is L minus 1. L equal to 2 power 8 equal to 256 minus 1 equal to 255. So the constant value equal to 255. And this is unsigned 8 and 0. The sample constant equal to ST. I mean the sample period is ST. Okay. And now this is connected to A. And this is from R. So this is to B. And the output is S. And to the gateway out block. Let's verify if our equation is satisfied or not. So this is R. So L minus 1 minus R, and this is the output. So okay, our equation is good. So we have implemented the equation good. So we shall run the model. So this is our image negative output. This is the input we have. See, this is only the R channel. We need to consider all the G and B channels to visualize the image negative more clearly. In a moment, we will consider all the 3 channels and will finally get the output color image. So this is only for the R channel. So now we shall consider all the 3 channels independently and then verify the output. So okay, I'm just readjusting this. So for the 3 channels, we need to implement the entire model as replicates. So I will copy and paste it. And for the video viewer, we need to have the 3 channels independently. So I'm going to image signal and the separate color channels. And also for the output, image signal and then separate color channels. So connect the outputs to each of the channel. And the inputs too. So this is the entire model for the image negative. Yes, now it's fine. You don't bother about this L minus 1, L minus 2 and L minus 3. These are renamed because no 2 blocks of the same kind must have the same name. So these are renamed automatically. Just I have given the name as L-1, so you can recognize that block easily. So now let's run for the output. First let us see the input and then now the output. Yes, this is the image negative output for the color image. I hope you have seen such kind of images. So for better understanding, you practice with some more images. You take human face and see for the output. So it will be very good for practice. And now we have another implementation, another kind of implementation, not just using this 255 minus R, that is this constant block and the addition subtraction block. So as here S equal to L minus 1 minus R. So as here is 8-bit image, that is S equal to 255 minus R. As from the image, this is the negative transformation, right? So what does it imply when you see the graph like this? Is it not the inversion, the entire inversion for the input? So instead considering these two blocks, I will just put an inverter in this place, and now I will implement the model for the image negative. So let me try for that. I will delete all these blocks. So I will keep an inverter. Yeah, again for simplicity I am considering the latency to be 0. Three inverters are required for our entire color model. So yeah, this is the another implementation for the image native model. So now let's run the model. So first input first, and for surprise we will see the output next. So the output, yes, we got the same output as of in the previous case, no change in that. So this is a second type of implementation, not using two blocks, the constant and the addition subtraction. See here, when you image the entire color implementation for an entire color image, you needed 6 blocks, 3 constants and 3 subtractors. So total 6 blocks you require. Whereas when you use the inverter, only 3 blocks are required. So thinking in the logical way and implementing in such a kind of way, you will reduce the blocks and save the area. As in VLSI, designing an FPGA, area is also one of the major constraints. You need to design such a high complex model within very small area ranging in nanometer square. You need to try for these kind of implementations, so it will be very easy to design any complex model. So I hope you understood this image negative concept and the implementation using system generator blocks good. And now let us proceed for the next technique in this section. Thank you.